Okay, right, today we are going to be talking about some different linear models in time series analysis. And I've cleverly labeled this cryptically with ARMA models. You may not know what that is right now, but by the end of today, you certainly will. Topics for today, we're going to start out by, sorry, let me move this. We're going to review, oh, hold on. Oh, it's the other instructor is late, I see. Apologies. Okay, so we're going to just briefly, we'll review white noise and random walks. Remember, those were really simple time series models. And then we'll start talking about some somewhat more interesting time series models, autoregressive, moving average, the combination of those two, autoregressive moving averages. And then we're going to revisit the autocorrelation function and the partial autocorrelation function and see how those can be used to identify the orders of AR or MA models. Okay, so recall from last Thursday that a white noise is a time series where all of its values are independent and they're identically distributed with a mean of 0. And we talked about how that distributional form for the errors is flexible, right? So here was an example where we were flipping a coin and taking twice that value, subtracting 1. And so we had a time series that was just bouncing back and forth between -1 and 1. The mean was 0, and there is no correlation over time. You can see that the autocorrelation function is 1 at 0 because it's correlated with itself, and it's essentially functionally at 0 everywhere else. And then we brought in this notion of somewhat more interesting white noise processes, and these are often referred to as Gaussian white noise or normal white noise. And here, those error terms, the WTs, are going to follow a normal distribution with a mean of 0 and some variance. We call that sigma squared. And we know that for Gaussian white noise sequences, the autocovariance at some lag k equals sigma squared, the variance of the error terms, if that lag is 0. And it's theoretically 0 if the lag is greater than or equal to 1. And similarly, the autocorrelation at some lag k is going to be 1 if k equals 0, and it's going to be 0 for any other lags greater than 1. And here was an example of Gaussian white noise. So this is just a simulation of a bunch of unit normals, a mean 0, variance 1, as the time series on the left, and the estimated autocorrelation function on the right. And you can see it's significant and 1 at lag 0, and it's functionally 0 at all other lags. We also briefly discussed random walks, and the idea is a random walk is basically a situation where the value today is the value yesterday plus some white noise. And here's an example of a random walk where the deviations, the WT here, are again just standard unit normals, mean of 0, variance of 1. And now you can see that from that autocorrelation function on the right, this has high autocorrelation out to many lags. In this case, they look like they're significant out to lag of 9 even, then they go away for a while. And we talked a little bit about this last week, that random walks are really flexible models, and you can fit these to a lot of different time series. You can make a random walk look like a linear trend or quadratic trend or some even sinusoidal thing, depending on sort of the amount of variance you allow for those normal deviates. So this motivates something called a biased random walk, or other people will call this a random walk with drift. And some of you may recall briefly being introduced to this notion when you took genetics. As people talk about gene frequencies following a random walk with drift. And we write a random walk with drift where the value today is what it was yesterday, plus some constant that does not vary over time. And I should say plus or minus some constant, plus some error terms. And this U parameter in this model is what we call the bias or drift term. And so every time step, you'll increase by some number of units U or decrease by U. Okay, so here's a graphical representation of a biased random walk. In this case, the bias is 1, and I'm using relatively high variance here. So on average, this time series is increasing by 1 step each unit, but it doesn't follow a strict linear trend, right? It's kind of bouncing up and down around that. And if you estimated a regression line through here, you'd find that the slope of this was essentially 1 and the intercept would be about 0. And here again, you can see that the autocorrelation function for a biased random walk has very strong autocorrelation out to long legs. If you difference a random walk, and we talked about that difference operator last week, that's going to yield a constant mean, or in time series literature, we often refer to a mean as a level, or some people even call it an intercept, U plus white noise. Okay, so here on the top, this is our biased random walk. Value today is yesterday, plus the bias, plus some error. And if we first difference this, that means we have to subtract x of t from both sides. So here I'm subtracting x of t, here I'm subtracting x of t. These two cancel out, so you're just left with the bias term plus the error, and here's the difference over here. So first differencing a random walk yields a constant level or mean U plus white noise. Okay, so here's that random walk that we saw 2 slides ago, where I've now differenced it. So that's what I'm plotting here on the y-axis. And the mean is 1, okay, plus some error. And if you look at the autocorrelation function of a first differenced random walk, it now no longer has strong autocorrelation at any lags greater than 0. Okay, so biased random walk itself has a lot of autocorrelation to it, but a differenced biased random walk does not. And the only difference here is that this now has a non-zero mean, right? The mean here is 1, it's not 0 anymore. And we will see biased random walks a lot in this class moving forward. In general, the idea is you could imagine comparing a model with or without that bias term and potentially testing for a trend up or down in a time series, right? So fit both of those models, do some sort of test to evaluate whether that U, that bias term, is significant or not, or whether it offers sufficient information to be included in the model. So we do that a lot in our world. Okay. Now I want to talk about linear stationary models. So white noise was stationary, but we talked about those random walks last week, and this time they are not stationary. And we're going to kind of dig into that a little deeper, and you'll be able to prove to yourself why that's in fact not the case. Okay. Thinking back to our linear decomposition that we talked about last week, we saw that linear filters are a really useful way for modeling that time series, right? We were able to sort of extract that, what we were calling a trend. And we used a simple moving average, but talked about, well, there'll be lots of other ways to do that. And we're going to extend that notion of kind of linear filters to a class, a large class of models, I might add, called autoregressive moving average models. And these models are widely used in ecology. And the idea here is that if we just think about the autoregressive part of this, and we'll kind of define this in a moment, it's really trying to model something about what's going on now. And we typically talk about the state of nature. What's happening today is a function of what's happened in the past. So we might be talking about growth of an animal, right? How big it was today is probably a function of how big it was yesterday, plus what it ate, and then minus what it excreted, digested, that sort of thing. We write out autoregressive models of order P, we talk about by shorthand saying AR and then parenthetically talking about the order P. is defined as such. So we have x of t, and then we have a coefficient here, phi1 x at t minus 2 plus phi2 x at t minus 2, etc., out to some order p. And this is now t minus p plus, again, some white noise component. So Wt is white noise, and what we assume here is that this autoregressive term, phi sub p, is not equal to 0 for an order p process. If it were, you'd essentially have an order p minus 1, right? If this term here was 0, this whole term would just go away, so this is really a p minus 1 AR model. So p here just determines how many of these terms you have in the model. Okay, so here's an example of some ARP models. Here's an AR1 model, and here's a case where the value today is 1/2 of what it was yesterday, plus some error. Here's an AR1 model with phi equal to 1. And this is just a random walk, right? If we put a 1 in front of there, this looks that's just our random walk model that we were talking about before. Here's an AR2 model. This one says today is minus 0.2 what it was yesterday, plus 0.4 what it was 2 days ago, plus an error term. And here's some just graphical examples of an AR1, AR2, AR3, AR4. And just by eyeballing these, I wouldn't be able to tell you which of those were of any of those orders. I could have just as easily guessed the one in the upper left was AR4 and the one in the lower right was AR1. Sorry, I'm going to move this for just 1 second. I'm really struggling with my windows here. Okay, so AR models tend to have high autocorrelation by their sort of nature, right? We're describing them as saying the value today is some function of the value yesterday, 2 days ago, 3 days ago, etc. So you would guess that they have relatively high autocorrelation. Okay, now this introduces this idea of stationary autoregressive models. And we talked last Thursday that stationary time series have the following properties, right? This was that there was no systematic change in the mean or the variance. So we shouldn't see something that's going along and then take some sudden jump and bounces around up here and then takes some sudden bounce, that sort of thing. We shouldn't see something that starts out close and then gets really big and starts, where the variance is changing. We don't want to see some trend like that biased random walk. And we don't want to see any sort of seasonality in there, some sort of, regular deviations. So that's nice. When we talked about on Thursday, though, our eyes are really horrible at actually determining which things are stationary just by eyeballing them. Okay, so we're looking for a more formal means here to actually ascertain whether or not something is a stationary ARP model. So to do so, we can write ARP models out using that backshift operator that we talked about. Okay, so here on the top, I've got an ARP model. It says 1 term, 2 terms, 3, 4, 5, etc., up to some number of p plus an error term. So what we want to do is we want to move all of the x terms to the left-hand side of the equation so that we just have the white noise term here on the right. So that's all I did here. I just moved everything over to this left-hand side. And now we know that if we can write this backshift operator to represent lagged versions of x. So here we don't want one, right? Because this is just x of t, it's not lagged, so that gets 1. Then we subtract phi1, x at t minus 1, well, that's just b, minus phi2, x at t minus 2, well, that's b2, etc., until we get out here to phi p, b to the p times x at t equals wt, or more generally, you could write it this way, and there's a typo. This should say b raised to the power p. We'll have to fix that. Okay, so here's a really compact way of writing an ARP model using the backshift notation. Okay, so now let's imagine that b is not a function. Instead, we're just going to think of it as a regular number or numbers. And if we do so, we can write out what's called the characteristic equation. So here's our ARP model, where again, this should be b raised to the power p, x at t equals wt. And to write the characteristic equation, we set this x equal to 1 and wt equal to 0, and we have this. So in order to be stationary, all roots of this equation must exceed 1 in absolute value. It's a little abstract right now, but we're going to show you an example that will help clarify this. Okay, so let's consider a simple AR1 model. Here we have x at t equals 1/2, x at t minus 1 plus some white noise. Okay, so we're going to write this out now using the backshift operator. So we move all the x terms over to the left-hand side of the equation. Then we have x at t, well, that's just x of t. 1/2, that's the same. X at t minus 1, well, that's just b times x of t. And then we can pull the x out of here. So we have 1 minus 1/2 b times x of t equals the white noise term. Okay. Algebra for days. I know, Brielle, you miss this stuff, don't you? It's like being a freshman in high school again. Lovely. Okay. So here we are. We've got 1 minus 1/2 b times x of t equals wt. I just transcribed that equation from the previous slide. Okay, so now we set x of t equal to 1 and wt equal to 0. And we've got 1 minus 1/2 b equals 0. And now we need to just solve for b. So we move the 1 to the other side, divide by minus 1/2, and we see b equals 2. So this model, back up, this model right here is indeed stationary because b exceeds 1, right? B equals 2, that's greater than 1, so this model is in fact stationary. Okay, what about this AR2 model that we looked at earlier? So x of t equals minus 2/10 times x of t minus 1 plus 4/10 times x of t minus 2 plus white noise. Well, we'll go through the same thing, right? We'll collect all of the x terms and move them to the left-hand side of the equation. That's here. And then we need to substitute all of our backshifted x's using b. So this is the same. This is the same. Now x at t minus 1, that's b at xt. 0.4, 0.4. X of t minus 2 is b2. X of t equals wt. Pull the x out of here. Okay, so now we have this quantity times x of t equals the white noise. Again, that's just repeated up here. Then we set this equal to 1, this equal to 0. Now we have a quadratic equation. It's getting better, Brielle. Now you have to remember how to solve a quadratic equation. So if you do this, you're going to find that b1 is approximately minus 1.35 and b2 is about 1.85. So this model is not stationary because only b2, this root right here, exceeds 1. b1 is actually less than 1, right? So this model is not stationary. Okay, what about random walk models? Here's your chance to follow along at home on a piece of paper, okay? Move the x terms over to the left side of the equation. Set x at t minus 1 equal to b of xt. Pull the xt term out by itself. Okay, that's what I've done here. Okay, we set x to 1, w to 0. We have this equation. And we move the 1 to the other side. Do the division here, b equals 1. So as I keep saying, random walks are not stationary because b equals 1, which is not greater than 1. Okay, so here's your way to prove to yourself and others 6 months from now when you can actually get together that random walks are not in fact stationary. So you can imagine doing this for a really high order model. You might need some software to help you solve that high order polynomial, but certainly for an AR1 model or an AR2 model, you can do this by hand easily. Okay, now we can think about some parameter space over which all AR1 models are stationary. And I'm going to focus on AR1 models here because in general, in a lot of ecological scenarios, AR1 lag order is enough. And later in the course, we're going to talk about all kinds of options for kind of AR1 models, or in a multivariate case, a vector autoregressive model. Okay, so here's our generic AR1 model, right? We've just got this parameter here instead of an actual number. Okay, well, same thing. Let's pull this x term over to the left-hand side of the equation. We're going to rewrite x at t minus 1 as b of xt. And then we're going to pull the x's out here. So we have the quantity 1 minus phi b times x of t equals wt. Okay. So for this equation, we know that here's our written in backshift notation. So let's set x to 1, w to 0, and solve for this equation. Okay, pull this 1 over to the other side, do the division. Here we see that b equals 1 over phi. And we know that in order to be stationary, this quantity has to be greater than 1. So in order for b equal to 1 over phi to be greater than 1, that only happens if and only if phi is between 0 and 1. Right? So if phi was 2, this would be 1/2. That's not greater than 1. If it's minus 1, that's going to be minus 1. Well, that's not greater than 1. So for all AR models, we know that phi be between 0 and 1. So if you see an AR1 model written out like this one up here in the upper left, if this phi were 2, you would know right off the top of your head that nope, that is not stationary because phi has to be greater than 0 and less than 1. Okay, well, what if phi was negative? All right, so here, what if we had an AR1 model that said x of t was minus phi times x of t minus 1 plus white noise? Well, same thing. Let's just go through this exercise one more time. Pull all the x terms over to the left-hand side. Substitute this with b of xt. Pull the xt terms out. So now we have 1 plus phi b times xt equals our white noise. Okay, so I've just rewritten that up here. We set this equal to 1, this equal to 0. Here's our equation. Bring the 1 over to the other side. Do the division. Now b equals minus 1 over phi. Okay, the only way we can get minus 1 over phi to be greater than 1 is if and only if phi is less than 0, but greater than minus 1. Okay, so to generalize that now for all AR1 models, we can say that AR1 models are stationary if and only if the absolute value of phi is less than 1. Okay, so here's your general rule for all AR1 models. You should just be able, from here on out, you write down an AR1 model or someone hands it to you and says, is that stationary? You can just look at it immediately and know, just by looking at this term right here. If the absolute value is greater than or equal to 1, it's not stationary. Okay, any questions on stationary AR1 models?
Yeah, I have a quick question. So is this stationary because if you have phi is less than, the absolute value of phi is less than 1, does that mean it approaches 0 as the mean? Is that true?
Not quite, but it means, Marcus, that it will never grow in any direction. And you would never get any sort of like exponential growth you can sit of. But basically it means that, yes, it's always some fraction of itself plus white noise. So it's going to kind of oscillate, in this case, around the value of 0, because that's the mean of the white noise terms. And every time it's less than 1, so it tends to be pulled back toward the mean. It's what oftentimes is referred to as mean reversion. And we will probably use that phrase quite a bit in this class, as a matter of fact. So yes, the tendency is to sort of be pulled back. So if there was a really large perturbation to an AR1 model, you managed to get a really large deviation, it will slowly work its way back down so that it's oscillating around a mean of 0. Yeah.
Got it, thanks.
Yeah. Anything else? Okay, let's move on. So let's compare some AR1 models just so you can kind of see some things about the behavior of them. So here's two different AR1 models that I simulated where the coefficient here is positive 7/10 or negative 7/10. And this is a plot of a realization of 50 time points. So this one looks like an autocorrelated model. These values generally follow along what they were. This model, on the other hand, tends to do this 2-point oscillation, right? It's going up, down, up, down, up, down, up, down, up, down. Very rarely does it not happen, but in general, it has this very seesaw pattern. Okay, here's two AR1 models, both of which are stationary. This one has a coefficient that's much closer to 1, and this one has a coefficient that's much closer to 0. So this one is definitely kind of wandering around through space, right? It's visiting all kinds. It started here about 1.8, down here, got all the way up to nearly 5. Now it's down to -3. Compare that to this one. This one is showing very little deviation in general around this. You could draw a pretty solid envelope in here. So I think it was maybe last time where I talked about smooth and choppy series. I think maybe Brielle had asked about this. So Brielle, we would talk about the one on the left as being more smooth and this one on the right as being more choppy. So, and you can imagine, right, the limit of an AR1 model as this phi term goes to 0 is just white noise. So, right, it would just look like it would just vary around 0 there as this term, excuse me, goes to 0. As this term goes to 1, it becomes a random walk. It wouldn't be stationary anymore. This thing would start to make over, if we let it go long enough, it would make really strong positive deviations and go way down low, that sort of thing. Okay. So let's now bring in this notion of autocorrelation. And we talked about that this is really measuring the correlation between some time series, x of t, and a shifted version of itself, that's some positive or negative lag. And that was symmetrical. It doesn't matter which way we shift it, right? The autocorrelation function is symmetrical. Here's the ACF for two of those AR models we just looked at. Here's the one where phi was positive 0.7, and here it's minus 0.7. Same time series I showed you before, right? This is that seesaw pattern. This one's smoother. Here's the autocorrelation function. It's 1 at 0, we know that by definition. And then here it's slowly kind of tapering off. For the one with minus 0.7, that's oscillating up and down, the ACF is also switching on off. Okay, you still see that it's significant kind of out here to lags 5, 6, 7, but it has this characteristic pattern. So if I just showed you this panel here in the lower right, moving forward, you should have some idea that the time series on the left, or it looks like something on the time series on the left, where it's switching on off. So that means each of the values must be largely trading. So we say that the autocorrelation function tends to oscillate up and down when that term is, when the AR1 coefficient is negative. Okay, let's look at the AR or the ACF for the models where we had phi 0.9, so approaching a random walk, and the one where it was 0.7. Okay, this one, strong autocorrelation out to many lags, here even out to like 15, it was significant. In this model here though, it looks like it's significant here, just barely significant there, and then bam, none of these are. Okay, so this one, this is that tendency, Marcus, where if something got away, it would basically kind of slap down to the mean and then sit there again. The other one, if you slapped it away, it would take quite a while to get back down to the mean. So when the ACF, or sorry, when that autoregressive coefficient, phi, is large, the ACF has a longer tail. Okay, now let's think back to that partial autocorrelation function. And this we talked about is measuring the correlation between some time series and a shifted version of itself, where we've removed all of that linear dependence between the intervening lags. Okay, so now let's think about, I'm showing you an ACF and a PCF for ARP models. So these are both AR3 models. And the only thing that is different is that this one has a positive AR1 coefficient and this one is negative, but otherwise it's the same value. So remember, this one's kind of smooth. It has this kind of long tail to it. This one is negative, so the time series is bumping up and down. And the ACF is also doing this kind of funny behavior. Here, the partial autocorrelation was positive, then it was negative, then it kind of goes away. Here it was strongly negative, then it was positive, and sort of goes away. Okay, here is now the PACF for 4 different ARP models. AR1, 2, 3, and 4. And does anyone see the link between the order P and lag in these PACFs? Sorry.
The number of lines. Let me see.
Say that again, Brielle.
It looks like the number of lines that are outside of that functionally zero thing.
Yeah, you're right. So right here, this is an AR1 model. The PACF shows significant autocorrelation at only lag 1. Here it's AR2, it shows it at significant correlation at lags 1 and 2. AR3, lags 1, 2, 3. AR4, lags 1, 2, 3, 4. Okay, so in general, we've seen that for ARP models, that ACF tends to tail off slowly, right? If we've got relatively high autocorrelation, we saw these kind of long tails to it. But the PACF cuts off pretty much exclusively after lag P. So this means if I presented you with a time series and you were thinking about, that does look kind of autocorrelated. I wonder if that's AR1 or AR7 or whatever. All you'd have to do is estimate, well, you might want to look at the ACF first, but then we want to be really interested in the PACF. And you can inspect that, and that would give you a pretty good idea of just by looking at the plot what the order of autoregression was in that AR model. Okay, so this is a useful kind of rubric for you moving forward. Now, I should back up here. Do you see how tight these confidence intervals here? In order to generate this example, I had to simulate a time series that was probably 1,000 units long and then estimate the ACF. So it got this really nice behavior from it. In practice, you're not going to have as well-behaved or lengthy time series. So these rules are, in theory, true, but in practice may not always be the case. So if you were presented with a PACF that looked like this, you might want to try AR1, AR2, and AR3, for instance, as possibilities. Okay, so these are theoretical ones here I've sort of showed you, sort of the best case scenario. But in practice, it's a good place to start. Okay, any questions on ARP models before we start talking about moving average models? No. Okay. In our world, on just ecology in general, you're not going to run across a lot of moving average models. Where you do find them tends to be in forecasting applications. But like I said, if you were going to comb the literature, ARP models would be way more common than MA models. Okay. We define a moving average model of order Q, or in shorthand, MAQ, as the following. It's our value today is a function of the error today, and then some coefficient times error 1 time step ago, another one 2 time steps ago, etc., up out to Q time steps ago. And again, here, the W's are white noise. So you can think about each of the XTs as some sum of the most recent error terms where they've all been discounted by some value. So therefore, all moving average processes are stationary. because they are finite sums of stationary white noise processes, right? So we talked about this before, that this term, WT, is stationary. So just multiplying that by some multiplier is still going to be, you may scale the overall variance, but it's not going to explode. It's not going to do some funny sign. It's not going to have linear trends, that sort of thing. So because this is just the sum of a whole bunch of white noise terms, and we know white noise is stationary, all moving average models are stationary. So that's nice. You don't have to go through that algebra. Okay, here's a couple of examples of some MA models. Here's an MA1, where it's the error today plus 7/10 of the error yesterday. Here's an MA2, where it was just, these two are equal weighted, but now it's -1 plus 7/10. And what can we say about these time series? I don't know. I mean, they're not particularly interesting. They don't show up as particularly noteworthy with respect to behavior. This one has some of that seesaw pattern because you've got a minus coefficient in here. So last time it was high. Well, if it's minus what it was before, that means next time it's got to be low, then it's got to be high, then it's got to be low, right? Sort of like the AR ones we're doing. So if you see this seesaw pattern in some time series, you would think that somewhere over here is a minus coefficient. It may be a minus AR coefficient, it may be a minus MA coefficient, but there's probably some negative coefficient in there driving this oscillatory pattern. Okay, let's now look at the ACF and PACF for moving average models. So here's that simple one where it was just theta was 0.7. Here's our other one where theta 1 was minus 0.7. Here it's 0.2, 0.3. There's the time series itself. Here's the ACF. Here's the PACF. Here's this time series, which definitely looks a little choppier perhaps than this one. ACF, PACF. So here's your quiz again. Here's now the autocorrelation function, the ACF, for 4 different MA models of order 1, 2, 3, and 4. And again, we're looking for a link between order Q and lag K. Come on, some brave soul has surely figured this out by now.
The graphs for the ACF, they cut off after the lag that's equal to the order Q.
Yep, exactly. So yeah, Logan, you nailed it. It's the analogy to PACF for ARP models. So here, this is a moving average 1. The last significant lag was lag 1. Moving average 2, the last significant lag was 2. MA3, the last significant one was 3. Oh no, look, here it's 4. This is that statistical artifact we talked about in last time, right? That you look at enough of these, you're going to find some random one somewhere that doesn't fit the pattern. Here's an MA4 process. ACF is, yep, 0 for everything beyond 4. Okay. So in general, we say that the ACF for moving average models tends to cut off after some lag Q, and the PACF will tend to do some wishy-washy, slowly decline to 0. There's no hard and fast rules there. So now you've seen how you can use the ACF and PACF for model identification. So, right, I hand you a time series, you can plot the ACF, plot the ACF or the PACF, and start to inspect at what lags those things are functionally going to 0 and get a pretty good idea of what the generating process was, what order it was. Questions on that before we do a little bit more algebra? No? Okay, it's pretty straightforward. Again, in our world, sort of environmental science, ecology, AR models very common, moving average not so common. Okay, this is a little bit of a gee whiz thing, but again, it's something to be able to stick in your back pocket. It's possible to write an ARP model as a moving average model with infinite order. This sounds really abstract at the moment, but we're going to go through that and show you. Okay, so here's a simple AR1 model. Okay, x of t, it's phi x of t minus 1 plus white noise. Well, this implies that x of t minus 1 is phi times xt minus 2 plus x of t minus, or wt minus 1, right? Which implies that x of t minus 2 is phi x of t minus 3, t minus 2, etc. Right? So this is just writing out every step of that model rather than keeping it generic. Okay, so there's nothing fancy here. So thinking about just this first part, where here's x of t as a function x of t minus 1, here's x of t minus 1 as a function x of t. Let's substitute this piece into this equation. Okay, well now we've got phi times, and this is the term for x at t minus 1 right here, right? So all I did was take this quantity, stick it down in there, and then do the multiplication. So now we have phi squared xt minus 2 plus phi w minus 1 plus wt. Okay, you could just keep doing this, right? Just keep doing those substitutions. So here's what we had before. You do it again, you do it again, and you keep doing this until you get way out here to some order k. So now we have, oh, sorry, that was here. And now we've got our last order. I just rewrote these, okay? So this one, they're descending orders, 4, 3, 2, 1, 0. Here it's 1, 2, 3, 4, etc. Up to some order k, plus then, right, we've got this little bit with the x here. So now we've got phi to the k plus 1 times this. In our AR1 model that was stationary, right, we started with that. We're considering stationary AR1 models. We know that the absolute value of phi has to be less than 1. That was the criteria for it to be stationary. This criteria implies that as k goes to infinity, right, so we're just going to crank this order up, right? We're talking about MA to an infinite order here. A number that in absolute value that's less than 1, so this is like between minus 1 and 1, raised to some huge power, let's call it infinity, is 0. And if you don't believe me, just open up an R window right now and take 0.9, raise it to 100 or something like that, you'll see. Okay, so that suggests then we had this long term here, right, where we've got all these moving average terms. And then we had this leftover bit from our autoregression. Well, we just said that this phi to the k plus 1 as a limit of k goes to infinity is 0. So this term will fall away, just goes to 0. So now we have an autoregressive process that's strictly a sum of the moving error components. So in order for this to be true, remember this order has to be large. You can't say, yeah, an AR1 looks just like an MA2 or an MA3 or even MA4. You have to make it a really big moving average model. Okay, there's another important aspect to moving average models, which is important really only in a computational sense. And that will become clear as we work through this. There's a notion of what's called invertibility with respect to moving average models. And we say that some moving average model of order Q is invertible if it can be written out as a stationary autoregressive process of infinite order without an error term. Okay, so the question is, here's our MA process. So value of X, it's the errors, white noise today, plus some fraction of yesterday, fraction of 2 days ago, up so that this is really big. So the question is, if we just switched these X and this W around, and we said, okay, WT equals X of T plus all of this, where we're gonna crank this order up to, again, like infinity, does this hold, right? So here we don't have any error terms on the other side. So that we're trying to say, can this be written as an autoregressive process with no error terms? So here we'd have X at T. The first time through, you'd have minus phi to the 1. Then it'd be minus phi to the 2, et cetera, et cetera. Well, why do we even care? Okay. The reason is because most of us use software to estimate parameters and models. I don't do it by hand. Some people probably get out a piece of paper and make that happen. Most of them are dead already. So in order to make this happen, software is typically set up so that it's going to figure out which of these solutions is actually invertible. Why does that matter? Okay, so here are 2 different MA models that are entirely equivalent with respect to their overall behavior. This one says X at T equals white noise today plus 1/5 of white noise yesterday. And here the white noise has a mean 0 and a really large variance. It's 25. This one says X of T is white noise today plus 5 times the error 1 time step ago. But the errors here are really relatively small. Mean of 0, minimal variance of 1. It's 1/25 of this. Okay, well, let's think about this top equation right here now. The variance for X of T is going to be given by this. So here's our equation. And the variance on this side of the equation has to equal the total variance on this side of the equation. Right, so the variance of X at T is going to be the variance of WT plus, and if you remember back to intro stats, right, it's now this term squared plus the variance of this. And we know the variance of this is 1/25. So here we have 1/25 times that variance. So this is 25. Then we say 1/25 times 25. Well, that's 1. The variance of X of T here is 26. Okay, great. Here's that second AR model or MA model I showed you, right? Where now it was the error today plus 5 times the error yesterday, not 1/5, but the variance of this is 1. So we do that exact same exercise. So the variance of X of T, well, that's going to be the variance of this plus now this term squared. That's 25 times the variance of that. So here we have the variance of WT was 1. 25 times 1 is 25. We add those up, it's 26. Okay, so the variance of X of T in both of these cases is 26. So if you have a piece of software and it can estimate, in general, what's the overall variance in X of T, and we're thinking about stationary models here. Both of those models, if it were 26, it would have a hard time deciding, well, should this be 5 times this value with a variance here of 1? Or should it be 1/5 this value with a variance of 25? So the idea here is that we want the one that's invertible, and the software will go ahead and make that choice for us. Okay, so let's rewrite that MA1 model. We're just going to switch the order around. We're going to bring the W to the left-hand side of the equation and this X to the other side. So we had to multiply all this by -1, right? Because this would be minus W minus X plus. So I just multiplied that by -1. Okay, and now we can substitute in our previous expressions for WT. So this is similar to like what we did before. Okay, so this implies that WT equals X of T minus theta, WT minus 1. Well, if we just -1 here, -1 here, -2 here. We can do the appropriate substitutions just as we did before. And now we have our white noise term is this long autoregression minus finally some remaining error term. Let's get back. the trick is, what do we want this to be? Okay, well, just like before, if we constrain the MA parameter theta, the absolute value of that, to be less than 1, then as order k goes way up to infinity, so we've got a really big model, minus theta to the k plus 1 times some error term is 0, because this term right here goes to 0. Okay, so that means that this equation we had before, we can drop off this last error. And now we have white noise is written as an infinite sum of autoregressive components without an error term. So this was our criteria to be invertible. We said that in order for an MA process to be invertible, we had to be able to write it as an infinite sum of autoregressive components with no error term out here. So let's see if I have that. Whoops. So then what that means is the software is going to search for a solution that it can do this. And in order to do that, we'll back up now for our two models. This model has a MA coefficient where the absolute value is less than 1. This one does not. So the software would return this as the solution to your model. Okay, even though these are essentially equivalent. So you will never need to go through this again unless you really want to. It's just to be thinking about in the back of your mind sometimes like, oh, wow, how does that actually work? I'm going to do that. Well, it's trying to figure out which of these is the invertible solution to MA models. Okay, questions about moving average models before we now talk about the package ARMA models, which are autoregressive moving average. No, okay. Whoops, I went right by it. Sorry about that. Okay, so autoregressive moving average models, or as we write in shorthand, ARMA with order PQ, are written thus. So we usually think about them in terms of some state X. We've got some number of moving or autoregressive components. Here's the first, second, third, fourth, fifth, etc., up to some order P that we designated here. Now we have to start adding in our moving average components. So we always start with the first one, then we have 1, 2, 3, 4, 5, etc., up to some order Q. Okay, so that's the combination of these two together, autoregressive moving average. We can write ARMA models using a backshift operator. So here we know that we've seen this before, right? This just says, gosh, this should be a P in here, there should be a Q in there. Right, so for order P, it's just going to be, well, this, if P is 1, then this is phi1 times b1, well, that's just x at t minus 1. And then here, this would be theta 1, b1, well, that'd just be wt minus 1. We can say then, based on that, that ARMA models are stationary if all roots of this side are greater than 1. And they're invertible if all the roots of this side are greater than 1 as well. And I'm not going to go through all of that algebra to do that, but that's basically the way you can do it. Okay, so here's some examples of ARMA models. All of these have a total order 4. So if you add up P and Q, they equal 4. Here's an ARMA 3-1. Here's an ARMA 2-2. Here's another ARMA 2-2. And here's an ARMA 1-3. And in particular, these three don't really look much different from one another. This one's starting to show a little bit of that choppy behavior, and that's largely because the AR1 coefficient here is negative. So it's going to go up and down with that oscillatory thing. And again, in environmental sciences, a lot of what we do, you're not going to see much ARMA PQ models in general. Certainly moving forward in this class, we're not going to focus on them in any great detail in sort of an applied context. but this is sort of your theoretical basis for the stuff you're going to be doing moving forward. If you took Stat 514 up on Upper Campus, you'd spend the first 5 or 6 weeks of class doing nothing but what we did in an hour today. It would be incredibly boring and you would just want to stab yourself, because I've been there. I took that class. So we're trying to get away from that in general. Okay, here's ACF, the autocorrelation function for ARMA PQ models, those same ones. Okay, so again, these are fairly stylized examples. I simulate a very long time series, and then what you see is that they tend to have this kind of long exponential decline to them. And in the case where the AR1 coefficient was negative, it's doing that oscillation. It's jumping up and down between -1 and 1. So anytime you see an ACF that does this behavior, you could probably bet a paycheck that the first AR coefficient was minus. Here now is the PACF for those same 4 models. And in general, these are tending to decline towards 0 much more rapidly than the ACF. And maybe here there's some suggestion that this one's going to 0 after lag 4. This one might be after lag 4. This one, well, there's 5. Oh boy, there's 7. This one now it's like maybe 3. So as far as our rubric goes, for ARMA PQ models, you're a bit out of luck. This is what the literature will tell you. Quote, they tail off slowly, whether it's the ACF or the PACF. So if you've gone ahead, I gave you a time series, you say, wow, I know what I'm doing. I can use the ACF function in R and I can use the PACF function in R and I'll fit those. If you get situations where there's no real definitive cutoff after some lag P in the PACF, or there's no definitive cutoff in after lag Q in the ACF, you're probably dealing with a mixture of our autoregressive and moving average components. Okay, questions on that before we just briefly talk about some non-stationary models? I know what the conversation is going to be at your dinner table tonight. I just know it. Okay. If the data don't appear stationary, right? They don't have a constant mean, or they've got some trend or some periodicity to them. We talked on last Thursday about how you can use differencing to remove either, difference once, you'll get rid of a linear trend, different twice, you can get rid of a quadratic trend, difference at lag equal to the period, like lag 12 for seasonal data will get rid of that seasonal bit for you. That notion of differencing to achieve stationarity motivates this kind of class of models that are called autoregressive integrated moving average, or we abbreviate those ARIMA models. That's the way this is pronounced. And ARIMA models we index with P for the autoregressive component, D for the number of differences, and then Q for MA. So P, D, Q. Integrated here suggests something like integration or derivation for the reverse case. The definition of an ARIMA PDQ model is that some time series follows that process, ARIMA PDQ, if 1 minus backshift raised to the differencing order here, D times x of t, is an ARMA PQ process. So that suggests if we difference something about an ARIMA process, we should get to an ARMA process. So some number of differences here should result in ARMA back from ARIMA. Okay, think about this ARMA 1.0 or AR1 process model, where here now I've got a quantity 1 plus phi times x of t minus 1 plus w, right? So here's our coefficient. Here I'm just calling it 1 plus phi. If phi is greater than 0, this is not going to be stationary. right? Because that would suggest this term will be greater than 1, and we know that that means it's not stationary. But if phi were minus 1/2, this would be a stationary model because this would just be 1/2. Okay, so there's an AR1 model, or ARMA 10. That's this. Those are equivalent notations for the same model. Okay, let's break this model out. So let's write this term out explicitly. So here we have x of t. Here's x at t minus 1 times 1. Here's x of t minus 1 times phi plus wt. If we move this term to the other side, we can write that then as a backshift operator, right? Because this is just, that's not shifted. This one is shifted, so that's b times x of t, and we've got that. So we said if we could write an ARMA model in this form, it's an ARIMA 1-1 process because we've done one differencing order there. So here's a case where, here's our ARIMA 1-1-0 model. This doesn't look particularly stationary. It seems to be drifting all over the place. Started up here, went high, now it's going way down here. This is not sort of behaving like it's around some mean. And here's the ACF for that model, right? It's significant positive lags, at least out to 20. Here now is the first differenced x of t. And this is in fact an ARMA 1-0 model, which is just the same as AR1. This looks a lot more like a stationary model, right? There tends to be some mean here that looks like it's oscillating around. It's not making massive deviations up here or massive deviations down here. And here you can see that the ACF is actually much better behaved. After, in this case, lag 1, we've essentially got no significant autocorrelation. And that's good because this is an AR1 model, right? So we shouldn't see much going on after that. Okay, so in review today, we went back, we talked about white noise and how white noise is in fact stationary. We talked about random walks, those are not stationary. We talked about autoregressive models and what makes an autoregressive model stationary and some of the diagnostics you can use to look for that. We discussed moving average models and how you can use the ACF to determine the order of moving average models. Then we talked about autoregressive moving average models. And again, how to use this ACF and PACF. And again, at the end, we talked a little bit about ARIMA models, but those in general are, again, not very common in our applications. You will see some of that, but typically, I'm just going to back up here in case, because oftentimes, if someone had this model and they were trying to fit a model to it, or sorry, this time series, and you were thinking about a model, knowing offhand just by eyeballing this, that doesn't look very stationary, a first thing might be to just difference it. And then you might look at that. So if you went ahead and software will do this for you, you could pass it this time series and it will estimate this to be an ARIMA 1-1-0 model. If you just said, I don't need the software to do that, I'm just going to first difference this thing and get this time series, then pass that to R and let it estimate what those terms are, it would come up with an ARMA or AR1 model. So oftentimes this operation is done by the user, the actual practitioner. Sometimes people tend not to do that, but it's usually best off if you have, you yourself as the analyst have some idea as to what's being done. Okay, that's all I have for today. Are there any questions about today's material or last week's material for that matter?
Hey, Mark. Oops. Hey,